Welcome to The Explainer. Today, we're diving straight into the invisible mechanics that govern our physical world. We literally interact with these physics every single day without even thinking about it. So, we're going to jump right into the granular details of how all of this actually works. Okay, let's dive into this. Have you ever wondered why you lurch forward when a bus suddenly stops? Think about your typical morning commute. You're standing on a bus, totally relaxed, reading a book or listening to music. And out of nowhere, the driver just slams on the brakes. What happens? Your whole body violently lurches forward. It feels like an invisible hand just shoved you, doesn't it? But there's no hand. It's just physics. Here is our master map for today's explainer, a beautiful, comprehensive breakdown of the laws of motion. We're going to unpack this whole thing piece by piece, starting from the absolute most basic, fundamental laws established centuries ago, all the way down to the immense forces required to launch a rocket into space. Whether you're actively studying Class 11 physics right now, or you're just brushing up on the fundamentals, this map shows us that these principles are absolutely everywhere. All right, Section 1, Newton's 3 universal laws and the foundation. To really understand the world around us, we have to start with the foundational rules discovered by Isaac Newton. These rules dictate how absolutely every object in the universe moves and interacts. Before we get lost in the mathematical weeds, let's rapidly step through this framework. First up, we have the law of inertia. Basically, this states that an object remains at rest or in uniform motion unless acted upon by an external force. Simply put, things like to keep doing whatever they're already doing. Second, we have a wonderfully simple but profound equation, F equals ma. And third, the famous principle of action and reaction. Let's look a little closer at that second one. So the crucial point is Newton's second law. Force equals mass times acceleration. This right here is the golden key to mechanics. It tells us exactly how much an object will speed up or slow down when you push it. Think about it. If you have a massive object, say a giant boulder, it requires a massive amount of force to accelerate it. But if you have a small mass, like a tiny pebble, it takes very little force at all. It's elegant, it's incredibly simple, and it mathematically proves exactly why you can't just casually kick a bowling ball down the street. And then, of course, we have the third law. Every action has an equal and opposite reaction. This tells us that forces never, ever exist in isolation. They always come in pairs. If you push on a wall with your hand, you might just feel like you're exerting force on the wall. But the mind-blowing truth is that the wall is actually pushing back on your hand with the exact same amount of force. Section 2, the inertia of everyday life. Let's shift our focus back to how that first law, the law of inertia, literally knocks you off balance. You see, inertia isn't just one broad concept. It actually breaks down into 3 very specific categories. First, we have the inertia of rest, which is the stubbornness of a stationary object to just stay put. Second, the inertia of motion, the intense resistance of a moving object to stopping. And third, the inertia of direction, which is the resistance of an object to changing the path it's currently traveling on. Let's see how this actually builds into real-world scenarios. Remember our bus example from earlier? Well, when a stationary bus suddenly starts moving, your body experiences the inertia of rest. Your feet move forward with the bus, but your upper body, it wants to stay right where it was, so you fall backward. Now, if you're in a rolling car that suddenly stops, that's the inertia of motion. The car stops, but you keep moving forward. And if that car takes a sharp, high-speed turn, your body feels thrown to the side. That's the inertia of direction, fighting to keep you moving in a straight line while the vehicle pivots around you. Section 3, mapping invisible forces. Now that we understand how our bodies react to these pushes and pulls, we really need to know how physicists actually calculate them. And this brilliantly illustrates the divide in how forces operate. On the contact side, we have forces that require actual physical touch to work. Think of friction rubbing against a tire, the tension in a pulled rope, the normal force of a table holding up your coffee cup, or physical weight. But then we have non-contact forces. These are kind of the spooky forces acting over a distance, like gravitational pulls keeping the planets in orbit, or electrostatic forces causing a balloon to stick to the wall. No touching required. To make sense of all these competing forces, physicists use something called a free body diagram. Consider a simple box sitting on a table. It looks like it's just sitting there, right? Doing nothing? But actually, it's a total battleground. Gravity's pulling the mass of the box down. That's weight, shown here as mg for mass times gravity. But why doesn't the box just fall right through the table? Because the table is pushing back up with an equal force. We call this the normal force, labeled n. A free body diagram is basically just a map of these opposing forces, completely stripping away all the noise to show us exactly what's pushing and pulling on an object.
Section 4. Friction, tension, and equilibrium.
So we've got forces pushing down, pushing up, and sliding side to side. Let's dive into the mathematics of it. When you look at this symbol, sigma F equals 0, you are looking at perfect harmony. This represents the equilibrium of forces. It means that when you add up all the vectors, literally every push, every pull, gravity, tension, the whole shebang, they perfectly cancel each other out. The net force is mathematically 0. When an object is in equilibrium, it is either perfectly still or moving at a constant, unchanging velocity. But what happens when we string objects together? Well, that introduces tension. Tension is the pulling force transmitted along a string, a cable, or a chain. Take a pulley system with multiple blocks. The tension isn't just isolated to one spot. The force actually travels through the connected system. If you pull on one end with force T1, that tension propagates right through the string, interacting with the masses and gravity along the way, represented by T2. It is an absolutely incredible way to redirect and transmit physical effort across a distance. Now let's slow things down a bit to talk about something that slows us all down: friction. Have you ever tried to push a really heavy piece of furniture? At first, it won't budge at all. That is static friction at work, governed by the formula Fs equals μs times n. You have to overcome a massive initial threshold just to get it moving. But once the furniture finally starts sliding, it suddenly gets a little bit easier to push, right? That's because you've transitioned to kinetic friction, which is Fk equals μk times n. Kinetic friction is inherently just a bit weaker than static friction. That exact tipping point, the maximum amount of static friction you can possibly apply right before the object finally snaps and begins to slide, is called limiting friction. And the formula reveals the fundamental relationship here. The coefficient of friction, mu, is equal to the force of friction divided by the normal force. Basically, the heavier the object, the greater the normal force pushing back, and mathematically, the harder it is to make that thing slide.
Section 5. Momentum and rocket motion.
All right, we've spent a lot of time down here on the ground dealing with friction. Now it's time to scale things up to space travel. Before a rocket can fly, it absolutely has to obey the law of conservation of momentum. This is a universal rule that states the total momentum of an isolated system before an event is exactly equal to the total momentum after the event. The equation, m1u1 plus m2u2 equals m1v1 plus m2v2. Okay, I know it might look a little intimidating, but the concept itself is beautiful. It means momentum is never, ever lost. It is only transferred from one object to another. The universe is like the ultimate accountant. The books always balance for sure. Now, what's really interesting here is how this bridges everything we've just learned. Take the completely simple act of walking. How do you walk? You push backward against the ground. And due to friction and Newton's third law, the ground pushes you forward. No friction, no walking, which is exactly why trying to run on ice is so tricky. Now scale that exact same logic all the way up to a rocket. A rocket doesn't push against the ground or the air. It actually pushes against its own fuel. By expelling massive amounts of gases downward at incredibly high speeds, the rocket gains an equal and opposite reaction upward. From your morning stroll to exploring the cosmos, it's literally the exact same physics at play. Which brings us to the end of our journey today. We've mapped out the laws, the inertia, the diagrams, and the momentum that quietly run our entire universe. So I want to leave you with a quick question to ponder as you go about the rest of your day. If every action truly has an equal and opposite reaction, what invisible forces are you setting into motion right now just by sitting in your chair? Thank you so much for joining me on this explainer, and keep exploring the fascinating world around you.